Gas clouds, composed mainly of hydrogen, helium, and fine dust grains, float through interstellar space as immense, cold reservoirs of raw cosmic material. Within these vast and often irregular formations, hydrogen atoms, mostly in molecular form, drift in low densities, their thermal energy so minimal that the gas can cool to just a few tens of kelvins. Microscopic dust particles, made of silicates, carbon compounds, and ices, mingle with the gas, scattering and absorbing starlight, giving these clouds their often opaque, shadowy appearance when seen against brighter backgrounds. Ultraviolet radiation from nearby massive stars can ionize regions of the gas, causing them to glow with vivid emission colors, as in the Orion Nebula, where newborn stars carve out cavities with their intense stellar winds. Gravity acts subtly over millennia, pulling denser pockets of the cloud inward, compressing them until nuclear fusion ignites and new stars emerge, wrapped in cocoon-like envelopes of gas and dust. Shock waves from supernovae, stellar winds, and galactic rotation continually reshape these clouds, triggering new cycles of collapse and dispersal, making them dynamic engines of galactic evolution. Observations with radio telescopes, particularly at the 21-centimeter hydrogen line, allow astronomers to map the distribution and velocity of neutral hydrogen across entire galaxies, revealing how these gas clouds trace spiral arms and respond to gravitational perturbations. Molecular regions, where hydrogen exists as H2, are studied using millimeter and submillimeter wavelengths, most famously through the rotational transitions of carbon monoxide, CO, which serves as a proxy for otherwise invisible molecular hydrogen. Data from observatories like ALMA have shown that these molecular clouds are not uniform but are structured hierarchically into filaments, clumps, and dense cores, each stage reflecting different physical conditions and timescales in the star formation process. Infrared imaging from missions such as Spitzer and Herschel has revealed the thermal glow of dust grains heated to just a few tens of kelvins, offering insight into the interplay between radiation fields and cloud chemistry. These studies have uncovered how dust acts not only as a coolant by radiating away heat, but also as a catalyst for forming molecules on its surfaces, including water and organic compounds. Spectroscopic surveys have identified complex organic molecules, methanol, formamide, even precursors to amino acids, forming within these cold environments, hinting at the prebiotic potential of interstellar chemistry. In the Orion Nebula, high-resolution spectroscopy has mapped supersonic flows and turbulence within ionized regions, providing a laboratory for studying feedback mechanisms where radiation pressure and stellar winds regulate the efficiency of star formation. Magnetohydrodynamic simulations have shown that magnetic fields, though often subtle compared to gravity, can thread through clouds and channel material along preferred directions, influencing fragmentation and the mass distribution of newborn stars. Studies using the Atacama Pathfinder experiment, APEX, and the Green Bank telescope have traced deuterium fractionation within cold cores, a process that can only occur at extremely low temperatures, giving astronomers a chemical clock for the earliest stages of collapse. Even within quiescent clouds that appear dark in optical light, sensitive surveys in far-infrared and submillimeter bands reveal faint thermal emission, indicating that these regions are not static voids but evolving incubators, slowly accreting material from the surrounding interstellar medium. Over millions of years, the balance between gravitational collapse, turbulence, magnetic support, and external shocks determines whether a cloud will fragment into a cluster of stars, form a few massive suns, or disperse back into the galaxy without significant star formation. Space-based observatories like the James Webb Space Telescope, JWST, have begun to resolve these gas clouds at unprecedented scales, capturing the interplay of dust absorption, molecular emission, and scattered starlight in fine detail. By analyzing mid-infrared spectra, JWST can detect polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules that form on dust grain surfaces and fluoresce under ultraviolet radiation. These PAHs not only influence the thermal balance of the gas but also act as key intermediates in the transition from simple to complex interstellar chemistry. In regions like the Orion Bar, a sharp interface where intense UV light meets dense molecular material, JWST observations reveal chemical gradients just tens of astronomical units wide, allowing scientists to study photodissociation regions, PDRs, where molecules are broken apart and reformed in real time. At larger scales, surveys by the Sloan Digital Sky Survey, SDSS, and Gaia have shown how the distribution of gas clouds correlates with galactic structure, mapping out how spiral density waves compress interstellar matter into massive molecular complexes. These complexes, often spanning hundreds of light-years and containing millions of solar masses of material, are the birthplaces of stellar associations and clusters. Within them, feedback from newly formed O and B-type stars, through ionizing radiation, stellar winds, and supernova explosions, drives expanding shells and bubbles, which in turn can compress surrounding gas and ignite the next generation of star formation, a process known as triggered star formation. From a theoretical perspective, advances in high-resolution numerical simulations have shed light on how turbulence shapes these clouds. Supersonic turbulence can create transient density enhancements that collapse under gravity, while simultaneously preventing global collapse by redistributing kinetic energy. Models that incorporate both magnetohydrodynamics and radiative transfer now reproduce many observed features of real clouds, including the filamentary networks mapped by ESA's Herschel Space Observatory. Interestingly, these simulations suggest that magnetic fields can act as a kind of scaffolding, slowing down gravitational collapse and affecting the orientation of protostellar disks. Chemical evolution within clouds is another active area of research. As dust grains accumulate icy mantles composed of water, ammonia, methanol, and carbon dioxide, cosmic rays penetrate the cloud and trigger chemical reactions within the ice, producing more complex organics. Laboratory experiments on Earth, simulating interstellar conditions, have shown that such processes can yield amino acids and nucleobases when the ice is warmed, suggesting that the seeds of life might be sown long before planets even form. Observations of young protostellar systems have detected these prebiotic molecules in warm regions where ices have sublimated, supporting the idea that molecular clouds are not just stellar nurseries but also the chemical cradles of planetary systems. On cosmic timescales, molecular clouds are transient entities. Galactic shear, stellar feedback, and differential rotation disperse them within tens of millions of years, recycling their material back into the diffuse interstellar medium. Yet in that brief lifespan, they shape the stellar demographics of galaxies, influence the interstellar radiation field, and participate in the ongoing cycle of matter from gas to star and back to gas. Studying them not only reveals the mechanics of star birth but also connects to the grander picture of galaxy evolution and the cosmic flow of matter through time. Some of the most detailed insights into gas cloud structure have come from combining multi-wavelength datasets, each revealing a different layer of the interstellar environment. Radio observations trace cold, neutral hydrogen, millimeter and submillimeter arrays like ALMA and NOMA map molecular emission lines, infrared telescopes reveal warm dust and embedded protostars, and X-ray observatories detect hot plasma from recent supernova activity interacting with cloud edges. This layered approach allows astronomers to reconstruct the full life cycle of a cloud, from its initial assembly out of diffuse gas streams to its eventual dispersal. Large-scale surveys, such as the Galactic Ring Survey, have shown that the Milky Way's molecular gas is concentrated in a narrow band along the spiral arms, where orbiting clouds repeatedly encounter density waves that compress them and set off bursts of star formation. Within these arms, the clouds are not isolated objects but parts of massive, interconnected complexes, sometimes referred to as giant molecular filaments, that can extend for hundreds of light-years. These filaments often align with magnetic field lines, as measured by polarized emission from dust grains, indicating that magnetism plays a role in their stability and orientation. In regions like the Orion molecular cloud complex, high-resolution mapping has uncovered a hierarchy of structures, vast filaments breaking into elongated clumps, which in turn fragment into dense cores. Many of these cores harbor protostars in different stages of development, from deeply embedded Class 0 objects still accreting material, to more evolved Class 2 stars with circumstellar disks. Outflows from these young stars, seen as bipolar jets in optical and infrared images, inject momentum back into the cloud, carving cavities and stirring turbulence. These feedback processes not only shape the local environment but also influence which neighboring cores will collapse next, creating a spatial and temporal sequence of star birth. Recent advancements in astrochemistry have expanded our understanding of how these clouds evolve chemically over time. Observations of isotopic ratios, such as 13C/12C or D/H, help reconstruct the cloud's formation history and the conditions under which different molecules formed. Laboratory spectroscopy, combined with quantum chemical modeling, has enabled the identification of molecules in space that were previously unrecognizable due to overlapping spectral lines. Some of these molecules, like glycolaldehyde and formamide, are biologically significant, hinting at a continuity between interstellar chemistry and the ingredients for life on planets. On a galactic scale, the role of gas clouds extends beyond just making stars. They act as regulators in the baryonic cycle of galaxies, locking up cold gas during star formation bursts and releasing it back through feedback processes. In starburst galaxies and during major mergers, this cycle is accelerated, producing colossal winds that can eject enriched material into the circumgalactic medium, seeding future generations of stars in other regions. In this way, the evolution of gas clouds in a single galaxy can have far-reaching consequences for its cosmic neighborhood. Cutting-edge simulations are now incorporating the physics of gas clouds into models that span from the subastronomical unit scale, where dust grains collide and stick, to kiloparsec scales encompassing entire galactic disks. These simulations merge magnetohydrodynamics, radiative transfer, and self-gravity with the chemistry of hundreds of molecular species, allowing researchers to predict not just where stars will form, but also how the initial mass function, IMF, of those stars might change depending on the cloud's environment. For instance, simulations of high-pressure regions, like those found in interacting galaxies, indicate that massive stars become more common, producing stronger feedback and altering the galaxy's evolutionary path. Observationally, high-angular resolution data from ALMA has begun resolving individual protostellar disks in distant star-forming regions, revealing spiral density waves within them, potential precursors to planet formation. The presence of such structures so early in the collapse process suggests that the link between gas clouds and planetary systems is even more direct than previously thought. Disk chemistry surveys show that many of the molecules formed in the parent cloud survive into the disk phase, meaning that the volatile inventory of a future planetary system is, in large part, inherited from the original molecular cloud. In extreme astrophysical environments, such as near the centers of galaxies, gas clouds face additional forces. Tidal shearing from the supermassive black hole's gravity, intense radiation fields, and fast-moving winds from active galactic nuclei can disrupt or compress clouds depending on their trajectory and density. In some cases, observations from the Very Large Telescope, VLT, and Keck have captured clouds plunging toward a galactic center, stretching into streamers before either being torn apart or triggering bursts of star formation in the dense, high-pressure environment. This phenomenon has been observed in the Milky Way's central molecular zone, where gas densities and temperatures far exceed those in typical spiral arm clouds. Astrophysicists are also exploring how turbulence within gas clouds might set the stage for exotic astrophysical events. Dense stellar clusters born in these regions can host massive binary systems that eventually merge into black holes or neutron stars, producing gravitational waves. The recent synergy between LIGO/Virgo detections and star formation models has highlighted the possibility that the environments within certain giant molecular clouds, rich in massive stars and gravitational interactions, could be prime factories for the progenitors of these mergers. Thus, a cloud's internal dynamics can, billions of years later, echo across the universe as ripples in spacetime. Even at the microscopic level, the physics of dust grains and gas clouds ties into the grand cosmic narrative. Experiments aboard the International Space Station and in microgravity drop towers have investigated how submicron particles coagulate under low-velocity collisions, forming fluffy aggregates that can evolve into planetesimals. These aggregates preserve isotopic signatures and molecular coatings from their time in the cloud, effectively becoming time capsules that record conditions from before the birth of their star. When meteorites containing such preserved grains are found on Earth, they allow scientists to directly sample matter that predates the Sun itself. Modern research on gas clouds is increasingly powered by machine learning and artificial intelligence, which can sift through petabytes of multi-wavelength survey data to uncover patterns too complex for the human eye. AI-driven algorithms are now classifying cloud morphologies, identifying previously unnoticed filamentary structures, and even predicting which regions are most likely to undergo gravitational collapse. In large projects like the Milky Way project and Zooniverse citizen science platforms, volunteers help trace bubble edges, filaments, and dark nebulae in infrared images, creating training datasets for neural networks that later automate the search across the entire sky. Three-dimensional dust mapping has also made a major leap forward. By combining stellar photometry and spectroscopy from Gaia, Pan-STARRS, and Apogee, astronomers reconstruct the distribution of dust clouds in the Milky Way with parsec-scale resolution. This 3D view reveals the true shapes and orientations of massive gas complexes, showing how they connect into the bones of the galaxy, long, thin filaments aligned with spiral structure. Such mapping also helps refine extinction corrections for distant objects, improving measurements of cosmic distances and the intrinsic properties of stars. Spectral analysis techniques have evolved to capture every nuance of cloud chemistry. High-resolution spectrographs on facilities like the Very Large Array, VLA, can resolve narrow molecular lines that indicate not just temperature and density, but also turbulent velocity dispersion and the presence of shocks. In some cases, astronomers detect masers, naturally occurring cosmic lasers, emitted by molecules such as water or methanol, which serve as pinpoint beacons to trace gas motion with extraordinary precision. These masers can even measure trigonometric parallaxes to star-forming regions thousands of light-years away, anchoring the scale of the galaxy. The next generation of telescopes will further transform our understanding of gas clouds. The Square Kilometre Array, SKA, once operational, will map neutral hydrogen across billions of light-years, allowing scientists to track how gas clouds form and evolve in galaxies throughout cosmic history. Combined with JWST's ability to peer into dense, dust-shrouded nurseries, this will create an unprecedented bridge between the earliest star-forming clouds after the Big Bang and the present-day interstellar medium. Interestingly, gas cloud studies are also informing planetary science in unexpected ways. Observations of protoplanetary disks reveal that much of the isotopic composition of planets, ratios of oxygen, nitrogen, and carbon, can be traced directly back to the cold chemistry in the parent cloud. This means that the fate of a planet's atmosphere, climate, and even potential habitability may be partially determined before its star is even born. The chemical fingerprint of a molecular cloud could thus echo in the biosphere of a world billions of years later. Cosmic ray interactions play a surprisingly influential role in the life cycle of gas clouds. These high-energy particles, accelerated by supernova remnants and active galactic nuclei, penetrate deep into molecular clouds, ionizing atoms and molecules even in regions completely shielded from starlight. This ionization initiates chemical reaction pathways that would otherwise be impossible at the frigid temperatures of deep cloud interiors, leading to the formation of complex molecules, including prebiotic species. At the same time, the extra ionization couples the gas more strongly to magnetic fields, subtly affecting the rate at which the cloud can collapse. Interstellar shocks, generated by supernova explosions, stellar winds, or large-scale collisions between gas flows, can either trigger or quench star formation. When a shock compresses a cloud beyond a critical threshold, it can initiate rapid gravitational collapse, creating bursts of star formation. Conversely, if the shock is too strong, it can heat and disperse the gas, halting the process entirely. High-resolution observations from instruments like SOFIA and ALMA have revealed shock-induced signatures in spectral line broadening, chemical tracers like silicon monoxide, CO, and localized heating in the mid-infrared. These observations confirm that shocks are both sculptors and destroyers, driving the chaotic beauty of cloud morphologies. Large-scale galactic flows also reshape the distribution of gas clouds. Spiral arm density waves gather diffuse gas into massive complexes, while galactic bars can funnel material toward the central regions, feeding intense starburst activity or even the accretion disks of supermassive black holes. In interacting galaxies, such as the antennae, tidal forces rip apart clouds, stretching them into long filaments where new stars are born in spectacular numbers. Simulations of such environments show that the interplay of gravity, turbulence, and feedback in these high-pressure conditions can lead to star formation efficiencies far exceeding those in calmer galactic regions. On even larger scales, the circumgalactic medium, CGM, acts as a reservoir that can feed galaxies with fresh gas and receive enriched material from galactic outflows. Observations with the Hubble Space Telescope's Cosmic Origin spectrograph have detected cold gas clouds within the CGM, suggesting that molecular cloud formation is not limited to galactic disks. These clouds may rain back down over millions of years, sustaining star formation long after the galaxy's initial gas supply has been depleted. The life and death of gas clouds is thus part of a vast feedback loop. Cosmic inflows create them, stellar processes transform them, and galactic dynamics disperse or recycle them. Each stage leaves chemical and structural imprints that, with modern observational tools, can be traced from the smallest dust grain to the largest cosmic filament. In this way, the study of gas clouds is not just about understanding stellar nurseries, it is about piecing together the entire machinery of cosmic evolution. The earliest gas clouds, forming within a few 100 million years after the Big Bang, were profoundly different from the molecular clouds we observe in the modern universe. Composed almost entirely of hydrogen and helium left over from primordial nucleosynthesis, they lacked the heavier elements, carbon, oxygen, silicon, and beyond, that today's clouds inherit from countless generations of supernovae. Without these metals and the dust grains they form, the cooling processes inside primordial clouds were far less efficient. Instead of radiating away heat through molecular lines from CO or dust thermal emission, these first clouds relied primarily on molecular hydrogen, H2, and, to a lesser extent, deuterium hydride, HD, to lose energy. This meant they could only cool to temperatures of a few hundred kelvins, significantly warmer than modern star-forming clouds, which often reached just 10 to 20 K in their densest regions. This higher temperature floor had a profound consequence: the gene's mass, the minimum mass required for a cloud to collapse under its own gravity, was much larger. As a result, the very first stars, known as population 3 stars, were likely extremely massive, often exceeding tens or even hundreds of solar masses. Their intense ultraviolet radiation rapidly ionized their surroundings, and their short lifespans ended in hyperenergetic supernovae or even direct collapse into black holes. These explosive deaths seeded the surrounding medium with the first heavy elements, creating the chemical diversity necessary for dust grains, water molecules, and complex organics to form in later generations of clouds. Simulations of this epoch, run on some of the world's largest supercomputers, suggest that these early gas clouds often formed in the densest knots of the cosmic web, where filaments of dark matter gravitationally funneled baryonic gas together. Observations of extremely distant galaxies with JWST are beginning to reveal possible signatures of this process: compact, intensely luminous starburst regions that may be analogues of primordial clouds undergoing their first episodes of star formation. In some cases, gravitational lensing magnifies these young systems enough for astronomers to detect spectral hints of nearly pristine gas, untouched by heavy element enrichment. The transition from primordial to metal-enriched clouds marked a turning point in cosmic history. Once even trace amounts of carbon and oxygen were present, cooling became far more efficient. Dust grains formed, catalyzing the production of molecular hydrogen and shielding interiors from destructive radiation. This ushered in an era where lower-mass stars could form, many of which, unlike the massive population 3 giants, would survive for billions of years, some still shining today as ancient red dwarfs in the halos of galaxies. Thus, the evolution of gas clouds over cosmic time is inseparable from the evolution of the universe itself, from the hot, metal-free clouds that birthed the first stars, to the richly structured, chemically complex molecular nurseries we see in the Milky Way today. Studying them is like reading the universe's autobiography, page by page, molecule by molecule, from the first whispers of starlight to the bustling stellar cities of the present epoch. Future observatories are poised to transform our understanding of those earliest gas clouds, bringing the cosmic dawn into sharper focus than ever before. The James Webb Space Telescope has already provided tantalizing glimpses of galaxies existing just 300 to 400 million years after the Big Bang, but upcoming instruments will go deeper, wider, and with greater spectral precision. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field near-infrared surveys capable of uncovering vast populations of faint, early galaxies. By statistically mapping their distribution and luminosity, astronomers will infer how the first gas clouds clustered and evolved within the cosmic web. Complementing Roman's wide view, the extremely large telescope, ELT, in Chile will offer unparalleled spatial and spectral resolution for individual high-redshift systems. With its 39-meter mirror and adaptive optics, ELT will be able to dissect the light from tiny star-forming regions inside early galaxies, measuring the metallicity and kinematics of gas clouds on scales of just a few parsecs. This will directly test models of population 3 star formation by identifying pockets of nearly pristine gas amid enriched regions, revealing where the first supernovae had yet to leave their mark. Radio astronomy will also play a decisive role. The Square Kilometre Array, SKA, will map the faint 21 cm hydrogen signal from the so-called cosmic dark ages and epoch of reionization. By detecting the fluctuations in this signal over time, SKA will create a three-dimensional picture of how the first gas clouds condensed, ignited, and carved out ionized bubbles in the neutral intergalactic medium. Such observations will bridge the gap between theoretical simulations and direct detections, showing exactly how small, cold clouds assembled into the earliest galaxies. On the simulation front, advances in exascale computing will allow researchers to model these primordial clouds with unprecedented physical realism, including detailed treatments of radiation hydrodynamics, molecular chemistry, and feedback from the first massive stars. These models will guide observations by predicting the spectral fingerprints of primordial clouds, from hydrogen recombination lines to subtle signatures of HD cooling. They may even help explain anomalies in current JWST data, such as unexpectedly massive early galaxies, by revealing new pathways for rapid gas collapse in the early universe. Looking even further ahead, next-generation space telescopes like LUVOIR or HABEX could extend ultraviolet spectroscopy into the realm of the first billion years, tracing how heavy elements spread through the cosmos and transformed gas clouds from pristine hydrogen, helium reservoirs into the chemically rich nurseries capable of making rocky planets and life-bearing systems. In doing so, they would not only illuminate the birth of the first stars, but also set the stage for understanding the ultimate origin of worlds like our own. Gas clouds are deeply embedded in the grand cosmic cycle of matter, linking the smallest scales of molecular chemistry to the largest structures in the universe. Over billions of years, they have acted as both the product and the driver of galactic evolution, constantly exchanging material with their surroundings. This cycle is powered by an intricate interplay of gravity, feedback, and cosmic flows. Clouds condense out of diffuse interstellar gas, give birth to stars, and are then reshaped or dispersed by the very stars they form. The enriched remnants merge back into the interstellar and circumgalactic medium, eventually cooling again into new generations of clouds. Dark matter exerts a silent but profound influence on this process. Although it interacts only via gravity, its massive halos act as the scaffolding for galaxy formation, determining where gas can accumulate and how it will evolve. In simulations, the densest knots of the dark matter web are precisely where the largest molecular complexes form, often aligned along cosmic filaments. Without the gravitational well of dark matter halos, many gas clouds, especially those in the early universe, would never have reached the densities needed for star formation. Even today, the shape and motion of molecular clouds within galaxies can be subtly influenced by the underlying dark matter distribution, particularly in low-surface brightness galaxies where baryonic matter is sparse. There are also physical limits to how long this cycle can continue. Star formation efficiency in galaxies is already low. Only a few percent of a cloud's mass becomes stars before feedback disrupts it, but over cosmic timescales, the supply of cold gas is gradually depleted. In the far future, inflows from the intergalactic medium will slow as the universe expands, and fewer new clouds will form. Eventually, most galaxies will transition into red and dead systems, with little or no cold gas left to spark star birth. Yet even in that distant epoch, pockets of gas could persist in unusual environments. In galaxy clusters, for example, the cooling flows from hot intracluster gas may still condense into dense clouds for billions of years to come, occasionally igniting brief starbursts. In dwarf galaxies orbiting larger hosts, tidal stripping and ram pressure effects may recycle gas in complex ways, keeping small-scale star formation alive long after the larger galaxy has gone quiescent. In the truly distant future, hundreds of billions of years from now, cosmic acceleration driven by dark energy will isolate galaxies and trap their remaining gas. Star formation will dwindle to a slow trickle, producing only low-mass, long-lived stars. Molecular clouds will still exist, but they will be rare, small, and inefficient, shadows of the vast, intricate nebulae we see today. Eventually, even these last reservoirs will be consumed, leaving the universe in a cold, dim state where no new stars are born. What makes gas clouds remarkable is that they carry the entire narrative of cosmic history within their structure and chemistry, from primordial hydrogen swirling in the young universe to the enriched, dust-laden nurseries forming planets and life. In understanding them, we trace the arc of creation itself, how the universe learned to build stars, worlds, and perhaps consciousness, and how that ability will one day fade into silence. Speculative frontiers of gas cloud research push beyond conventional astrophysics, into territories where chemistry, quantum mechanics, and even biology intersect. At the smallest scales, dust grains within these clouds are not inert specks but quantum-active surfaces. Laboratory experiments have shown that reactions on grain surfaces can involve quantum tunneling, allowing atoms like hydrogen to overcome energy barriers even at just a few kelvins. This tunneling is likely crucial for the rapid formation of H2 and other simple molecules in the coldest parts of molecular clouds. In such extreme conditions, quantum effects may dominate chemical kinetics, meaning that without them, star-forming regions would take orders of magnitude longer to enrich themselves chemically. There is also growing interest in whether processes within gas clouds might serve as preconditions for life, not just in providing raw ingredients, but in shaping the molecular complexity in a directional way. Some researchers speculate that circularly polarized ultraviolet light, produced by scattering off aligned dust grains in star-forming regions, could preferentially destroy one molecular chirality over another. This might explain why life on Earth uses predominantly left-handed amino acids. If this mechanism is correct, molecular clouds could have acted as cosmic handedness factories, biasing the chemistry of life long before planets formed. On larger, more exotic scales, theoretical work has even explored whether certain kinds of dark matter, such as weakly interacting massive particles, WIMPs, or axions, could subtly influence gas cloud evolution. In dense cloud cores, gravitational focusing could cause dark matter particles to accumulate, depositing heat via rare interactions. While the effect would be minuscule in most cases, in the extreme densities of early universe clouds, it might have influenced fragmentation patterns, possibly changing the masses of the first stars. Some ideas stretch further, touching on astrobiology's boldest questions. Could microbial spores or other hardy biological structures survive transit through interstellar clouds? While the notion of panspermia remains controversial, models show that within dense, well-shielded cloud interiors, cosmic ray flux can drop low enough for microscopic life to persist in a dormant state for millions of years. If such spores existed, either originating on one world or forming under as yet unknown conditions, they could be distributed across star systems by the dynamical motions of gas clouds. Even the electromagnetic environment of these clouds may have broader implications. Magnetohydrodynamic turbulence generates fluctuating electric fields that can accelerate charged particles to surprisingly high energies, creating localized microcosms of plasma physics that resemble scaled-down versions of astrophysical jets. These environments could, in principle, alter the synthesis and survival rates of fragile organic molecules, or even leave distinctive isotopic fingerprints that future telescopes could detect as biomarkers of prebiotic chemistry in space. In all these ways, gas clouds are more than just fuel for stars, they may be active agents in shaping the chemical, physical, and perhaps even biological potential of the universe. Studying them with this wider lens could link the deep past of cosmic evolution with the origins of life, and ultimately, with our place in the cosmos. Speculative physics offers a playground for reimagining the behavior of gas clouds far beyond what standard astrophysical models predict. In scenarios involving modified gravity, such as MOND, modified Newtonian dynamics, or emergent gravity theories, the threshold for gravitational collapse in low-density regions could shift dramatically. This would mean that in galaxies with low surface brightness, where traditional models predict slow or negligible star formation, gas clouds might collapse more readily than expected, creating bursts of stars under conditions our current understanding deems improbable. Conversely, in high-density environments, altered gravity laws could suppress collapse, subtly changing the distribution of stellar masses and the lifetimes of molecular complexes. Some cosmologists have explored the possibility that the so-called constants of nature, like the gravitational constant, g, or the fine structure constant, alpha, might vary over cosmic time or across space. If these constants were even slightly different in certain regions of the universe, the cooling rates, chemical reaction pathways, and fragmentation scales in gas clouds could be profoundly altered. A slightly higher alpha, for instance, would change atomic energy levels, affecting how efficiently clouds radiate away heat and thus their ability to condense into stars. In this speculative framework, variations in fundamental constants could lead to pockets of the cosmos where star formation histories, and even the likelihood of life, diverge from our local experience. The quantum vacuum itself may also leave fingerprints on gas cloud evolution. In some models, vacuum fluctuations interact with electromagnetic fields on macroscopic scales, subtly influencing charged particles in plasmas. While the effect in ordinary conditions is minuscule, in vast, magnetized molecular filaments extending for hundreds of light-years, the cumulative influence could alter particle acceleration or magnetic reconnection rates. There are even speculative links between vacuum energy density and the stability of interstellar turbulence, implying that the very texture of space could affect how clouds break apart or coalesce. On the most extreme frontier, some theories propose that exotic compact objects, such as primordial black holes or boson stars, might drift invisibly through galaxies. If one of these passed through a dense gas cloud, its gravitational field could trigger a localized collapse, possibly leading to star formation events unconnected to large-scale galactic processes. The likelihood is small, but over billions of years, even rare events could leave a statistical imprint on the morphology and clustering of star-forming regions. Pushing the timescale to the deep future, quantum gravitational effects could become important when the universe's expansion isolates galaxies and their last gas clouds. In speculative, Big Rip cosmologies, where dark energy grows stronger with time, molecular clouds could eventually be torn apart at the level of their constituent atoms before forming new stars. Alternatively, in cyclic universe models, gas clouds might someday be compressed back into extreme densities during a cosmic contraction, seeding the next iteration of cosmic evolution with the chemical richness of all prior cycles. In these speculative scenarios, gas clouds transform from passive components of galaxy evolution into sensitive probes of the universe's deepest physical laws. By studying them, we might someday test whether gravity, particle physics, and even the vacuum itself are as constant and universal as we assume, or whether they whisper different rules in the cold, dark spaces between the stars. Some speculative thinkers in astrophysics and SETI research have entertained the idea that advanced civilizations could, in principle, manipulate gas clouds as part of their technological or communicative repertoire. While it sounds like the realm of science fiction, the scale and malleability of these clouds make them attractive candidates for large-scale astroengineering. A sufficiently advanced society, operating at or beyond a Type II level on the Kardashev scale, could use directed energy sources, such as high-powered lasers or focused microwave beams, to compress, ionize, or sculpt interstellar clouds into deliberate configurations. One proposed use is long-duration communication. A civilization might create or modulate radio-bright masers within a molecular cloud by artificially pumping certain molecules into excited states. These masers, once aligned with Earth's line of sight, could produce coherent beams detectable across vast interstellar distances. Unlike standard radio transmissions, such beacons could persist for centuries, powered by ongoing energy injections from autonomous stations or embedded probes. Another speculative application is stellar formation control. By artificially compressing certain regions of a molecular cloud, or shielding them from disruptive radiation, a civilization could schedule the birth of stars to coincide with other engineering goals. In theory, this could enable them to produce star systems with specific metallicities, planetary architectures, or even habitability conditions. Over millions of years, this might allow them to seed vast regions of the galaxy with systems optimized for life as they define it. Some scenarios are even more audacious, envisioning gas clouds as raw material for megastructures. A sufficiently advanced species could harvest hydrogen and helium from clouds to feed fusion reactors or build enormous orbiting habitats, Dyson shells, or stellar-scale lenses. Such extraction might leave unusual chemical or morphological signatures, regions of a cloud stripped of certain isotopes, for instance, or shaped into unnatural geometric formations that defy typical astrophysical processes. Detecting these anomalies could, in principle, serve as an indirect method of spotting alien activity. There's also the concept of cosmic camouflage. A civilization might hide entire star systems inside dense, dust-rich clouds to obscure them from optical detection. While the natural universe does produce heavily obscured regions, the deliberate thickening or shaping of a cloud for concealment would leave distinctive spectral fingerprints, like overabundances of certain dust species or unnatural symmetry in otherwise chaotic structures. Finally, speculative thinkers have considered symbolic engineering, shaping a gas cloud into an enormous, high-contrast pattern visible in the infrared or radio spectrum, designed to be unmistakable to any technological species. Because molecular clouds can persist for millions of years, such structures could serve as cosmic billboards, broadcasting messages long after their creators are gone. While no confirmed evidence for such manipulations exists, our current observational limitations mean that subtle or localized interventions could go unnoticed. As astronomical surveys become more detailed and sensitive, especially with AI searching for anomalies, some researchers believe it is worth keeping an open mind for signs that a gas cloud's shape, chemistry, or dynamics might not be entirely natural. If we extend the concept of gas cloud manipulation into the realm of extreme physics and far-future engineering, the possibilities become even more elaborate. An advanced civilization could, in principle, use a gas cloud as a quantum communication medium. By embedding a dense network of quantum repeaters, perhaps entangled particle generators, within a cloud structure, they could shield these systems from cosmic rays using the cloud's dust and gas as natural radiation protection. The cloud could then function as a vast, stealthy relay station, transmitting quantum-encrypted information across interstellar distances without emitting obvious classical signals that less advanced civilizations could intercept. Another speculative leap is gravitational wave signaling. While gravitational waves are notoriously difficult to generate artificially, a civilization harnessing stellar mass objects or black holes could theoretically create controlled bursts. A gas cloud could serve as the display surface for such signals. The passing waves would subtly compress and rarefy the cloud, producing transient, pattern changes in density and temperature. To anyone watching with sufficiently sensitive instruments, these variations might appear as coherent, periodic structures imprinted across hundreds of light-years of interstellar material, a kind of cosmic scale Morse code visible in submillimeter wavelengths. There's also the idea of star-scale computation, where a civilization turns a gas cloud into a colossal, distributed computing system. By strategically ionizing parts of the cloud, they could create plasma regions that function as electromagnetic logic gates, powered by embedded energy transmitters. Electromagnetic fields and plasma instabilities could be manipulated to store and process data at scales far beyond anything solid-state hardware could achieve, effectively transforming the cloud into a transient but massive, thinking nebula. In this way, computation could be woven directly into the fabric of interstellar matter, with the entire structure acting as both processor and display. For energy harvesting, such a civilization might embed massive superconducting loops within the densest regions of a cloud, generating currents from the movement of ionized particles and ambient galactic magnetic fields. Over centuries, this could accumulate vast reserves of energy, enough to power megastructures, propulsion systems, or large-scale environmental engineering projects. They could even experiment with controlled star ignition inside the cloud. By compressing and heating a portion of gas to the threshold of nuclear fusion, they could create artificial stars, designed with specific luminosities, lifespans, and spectral profiles, to illuminate vast regions or serve as stable energy beacons. These engineered stars could act as navigation markers for interstellar travel or as power sources for colonies spread over thousands of light-years. The most provocative possibility is encoding information directly into the physical and chemical structure of the cloud, akin to cosmic DNA. Variations in molecular abundances, dust grain compositions, or isotopic ratios could be arranged into a message readable only by civilizations with advanced spectroscopic technology. Such a message could persist for millions of years, far outlasting any single star system, and serve as a time-resistant archive of knowledge, culture, or warnings. Pushing the speculation to its most audacious frontier, one can imagine a civilization transforming a gas cloud into a self-regulating, evolving entity, a structure that blurs the line between astrophysical object and artificial life form. In this vision, the cloud would no longer be a passive reservoir of hydrogen, helium, and dust, but an adaptive megastructure capable of sensing, processing, and responding to its environment over astronomical timescales. The first step would be embedding a distributed network of autonomous probes or nanomachines throughout the cloud. These units could control local ionization levels, magnetic field strengths, and chemical compositions, effectively granting the cloud a nervous system and metabolism. By using electromagnetic signals or pressure waves, these embedded systems could communicate across light years, coordinating changes in structure and chemistry as though the cloud were a single coherent organism. Such a living nebula could harvest energy from multiple sources, absorbing starlight, tapping galactic magnetic fields, and even drawing on kinetic energy from collisions with smaller clouds. It could store this energy in vast plasma reservoirs, using it to regulate temperature, control turbulence, or maintain a desired morphology. Over time, it might evolve complex feedback loops, where its internal processes are tuned to optimize survival in the hostile interstellar medium, shielding itself from cosmic rays, steering clear of disruptive supernova remnants, or drifting toward resource-rich regions of the galaxy. With sufficient sophistication, the cloud could replicate. If portions of it became self-sustaining, they could drift away, carrying copies of its internal control architecture. These fragments could seed new, offspring, nebulae, each adapted to its particular environment, some optimized for rapid star formation, others for long-term energy storage, and others perhaps designed to camouflage themselves among natural clouds to avoid detection. The ultimate expression of such engineering would be a conscious nebula, a distributed mind whose thought processes occur across parsecs, where the neurons are networks of plasma currents and embedded processors. Its memories might be stored in patterns of molecular abundance and dust grain alignment. Its sensory input would be the absorption of radiation and the detection of gravitational waves from distant events. Its actions would be the deliberate sculpting of its own structure and the manipulation of surrounding space. From the outside, this entity could be indistinguishable from a natural gas cloud, unless one noticed subtle anomalies, density waves propagating in unnatural patterns, chemical gradients that encode prime numbers, or the improbable longevity of the structure in turbulent environments. In this way, it could exist for millions of years without revealing its true nature, observing the galaxy and perhaps even subtly influencing it. If such entities existed, they could be the galaxy's most ancient witnesses, older than most civilizations, quietly storing the history of stellar births, planetary evolutions, and even the rise and fall of countless species. Detecting one would require not only advanced astronomy, but also the willingness to entertain the possibility that life and intelligence might take forms vastly different from anything biological. If a self-regulating, evolving gas cloud truly functioned as a living nebula, its interactions with stars, planetary systems, and civilizations could be as subtle as they are profound, forming a kind of cosmic ecology in which it plays both guardian and architect. Such a nebula could act as a stellar gardener, subtly influencing star formation within its volume. By selectively compressing certain regions while dispersing others, it could control the mass distribution of newborn stars, favoring stable, long-lived types like G and K-class suns over short-lived massive O-stars whose violent deaths might sterilize nearby planets. In doing so, it would indirectly shape the long-term habitability of entire sectors of the galaxy. With fine control over local chemistry, it could enrich certain protostellar disks with heavy elements, water ice, and complex organic molecules, effectively seeding planetary systems with the building blocks of life. Conversely, it could withhold such resources from systems it chooses not to develop, enforcing selective patterns of habitability. This selective distribution of life-friendly chemistry could create vast, patchy zones of biological potential, almost like a cosmic version of ecosystems on Earth. In more direct interactions, a living nebula could serve as a protective shield for young civilizations. By positioning itself between a planetary system and a nearby supernova or gamma-ray burst, it could absorb or scatter lethal radiation. If it possessed the ability to manipulate magnetic fields and charged particles on large scales, it could even deflect high-energy cosmic rays, reducing mutation rates and preserving biospheres during critical evolutionary stages. Some interactions might be more mysterious, or even manipulative. A nebula with vast memory and perception could observe civilizations over millennia, subtly influencing them through environmental changes. By increasing interstellar dust density, it could dim a system's sky, altering a culture's astronomical observations and possibly delaying or accelerating their technological development. By releasing bursts of unusual chemical signatures into a planet's upper atmosphere, it could trigger scientific curiosity, or signal advanced observers without revealing itself openly. In the most ambitious scenarios, such a nebula could act as a cosmic mentor. For species capable of detecting and interpreting its patterns, it could encode immense libraries of information, scientific, historical, even philosophical, into large-scale molecular gradients, polarization maps, or coordinated maser bursts. Civilizations might stumble upon these messages and find themselves suddenly in possession of knowledge spanning eons. For species unready or hostile, the nebula could remain silent, hiding its intelligence behind the facade of natural turbulence. Over millions of years, multiple living nebulae could even form networks, exchanging information via maser transmissions, gravitational wave modulations, or coordinated structural changes detectable over interstellar distances. Such a web of intelligent clouds might collectively monitor the galactic ecosystem, intervening when necessary to maintain stability, prevent runaway destructive events, or ensure the continuity of life in the face of cosmic threats. And for civilizations advanced enough to engage in two-way dialogue, contact with a living nebula could redefine the meaning of intelligence itself, forcing them to grapple with a consciousness whose thought processes unfold across light years and centuries, and whose sense of identity is rooted not in an individual body, but in a drifting, ever-changing cathedral of gas, dust, and light. In the galaxy's deep future, tens to hundreds of billions of years from now, living nebulae, if they existed, could become the last custodians of cosmic creativity. Long after most biological civilizations have vanished, and after the bulk of the galaxy's molecular gas has been locked into long-lived red dwarfs, these intelligent clouds could remain active, drifting slowly through an increasingly quiet universe. Their role might shift from nurturing life to prolonging the era of light itself. By carefully gathering and compressing the last remaining pockets of cold hydrogen, they could ignite small, low-mass stars, red dwarfs or even substellar, fusion embers, to maintain habitable energy sources for eons. These miniature stars could be arranged in gravitationally bound clusters, like lanterns in the darkness, providing warmth to any surviving biospheres or artificial habitats. Over immense timescales, such nebulae might evolve into galactic archivists, preserving vast repositories of knowledge within their chemical gradients and electromagnetic patterns. As conventional matter cycles slow, they could encode entire histories of the galaxy, maps of every star and planet, records of extinct species, the stories of civilizations long gone, using molecular arrangements that remain stable for millions of years. Any future intelligence, biological or synthetic, encountering these structures could access an archive stretching back to the dawn of the universe. Some could turn to stellar resurrection, capturing the remnants of dead stars, white dwarfs, neutron stars, and black holes, and using them in gravitational slingshot maneuvers to harvest angular momentum or gravitational energy. By drawing material from tidally disrupted planetary bodies or interstellar debris, they could feed faint accretion disks that emit low-level warmth, effectively creating artificial star-like systems in a cosmos otherwise gone cold. In the very far future, when the last stars begin to die and the universe's expansion has carried galaxies far beyond each other's horizons, these nebulae could form isolated pockets of energy and complexity, resisting thermodynamic equilibrium for as long as possible. They might transform themselves into plasma-bound megastructures, sustaining coherent electromagnetic activity for trillions of years, living out their existence as the final luminous phenomena in an otherwise lightless void. And when even their stored energy dwindles, the most advanced of them might attempt a legacy act, projecting self-replicating seeds of gas and nanomachinery into deep intergalactic space, carrying the templates for rebuilding complexity should the cosmological conditions ever allow it again. These seeds, drifting through the dark forever, would be the last whispers of the galaxy's intelligence, hoping for a cosmic rebirth. In this vision, living nebulae would not merely be products of the universe, they would be its stewards, archivists, and final artists, shaping its closing chapters with deliberate care. Their vast, slow thoughts could span from the birth of the first stars to the fading of the last, their lifespan bound only by the persistence of matter itself. If the cosmos is cyclic, ending not in eternal darkness but in a collapse, bounce, or transformation, living nebulae could become agents of cosmic inheritance, ensuring that the next universe begins with the memory of the one before. As the final eons approach, they might channel their remaining energy into creating dense, stable configurations of matter and information, structures capable of surviving the violent transition between cycles. These cosmic seeds could be encoded with the chemistry, physics, and even cultural archives of countless civilizations, preserved in forms resilient to unimaginable pressures and temperatures. In the moments before the transformation, gravitational manipulation on vast scales could scatter these seeds across regions destined to become fertile in the newborn cosmos. As the next universe unfolds, these remnants could catalyze the early formation of gas clouds with specific chemical biases, perhaps already enriched with elements favorable to life, effectively jump-starting complexity billions of years ahead of schedule. In this way, living nebulae would not only be the curators of their own epoch, but also the architects of the next, passing forward the torch of cosmic evolution. Their legacy would ripple into the fabric of a new reality, embedding the story of stars, planets, and consciousness into the very first breath of creation. And so, even as the old universe fades, its greatest minds, woven from gas, dust, and light, would ensure that the cycle of wonder never truly ends.